My name is Teddy Coughlin. I'm with Beta Technologies. I am a flight test maintenance team member. I'm also a pilot, and we're here for the first time at Oshkosh with some Beta aircraft. We have two of these here at Oshkosh. We have one that's flying in the shows, and then we have this here for static display. We're gonna do a walk around and show you about this aircraft, November 916 Lima Foxtrot. This is our first off the production line, production intent aircraft. We're now just through our fourth one. This came off the line in November, and it has done a full United States tour to California and Florida and back, and now we're out here with it at Oshkosh showing off. When it was first produced, it was a cargo variant, so it would have a bulkhead right here behind the seat, and that was all for cargo. We did a bunch of missions like that first, and then we revamped it for our passenger mod. We flew it to New York City and did the first passenger flight through New York City with it, and now we here have it open for everybody to sit in it and try it out. It's actually really cool that we have it available for people to get in, because it's like testing all of our components. We'll see what breaks, what wears first, and all that kind of stuff. As a maintainer on the road for this aircraft, it's a little different than flight test maintenance that we do at home. So flight test maintenance, we're loading it up with weight, doing CG changes and envelope expansion, all by the book and everything. But here on the road, we're operating it just like a normal aircraft. So it's kind of cool. The only liquid we have on the aircraft is brake fluid. So we don't have tanks, bladders, fittings, just minimal brake hoses, no pumps, no boosters, no valves, none of that. We meet a lot of people and they have EVs, Teslas, Chevy Volts, Ford Lightnings, that kind of stuff. And they always mention that the tires are really annoying and the windshield washer fluid is really annoying. And it's the same thing for this aircraft, is that on the road, my biggest thing I always think about is wheels, brakes, and tires. And what's funny is we're not doing that any more than any other aircraft. It's just the only thing we have to pay attention to. So it seems like that's a big problem, but it's really not. It's just wearing tires like a normal aircraft, but it really sticks out as the heavy hitter maintenance item. So on the road operations is really smooth for us. It's super cool. We carry around a charger that looks like that one right there. That's our mini cube. That plugs into a Hubble connector just like a GPU would at FBOs. So when we roll up to an airport, we unload that from the aircraft. We can plug it right into the hangar there, the FBO, where they would have a GPU for a jet, and we plug it into the aircraft and charge the aircraft. It's an 800 volt system. We have 5 high voltage batteries underneath, 1, 2, 3, 4, 5, going all the way back. The aircraft can fly on 5, 4, or 3 packs depending on your mission. So if you wanted optimum range, but you don't need that much payload, you can do 5 packs. That's what we do for ferrying the aircraft. For alternate missions such as airshow flying, where we're just doing short circuits and we want the most maneuverability out of the airplane, we have it on 3 packs. So what that does is that removes about 1,200 pounds of weight that you don't need because you don't need the range. So yeah, like I was saying, those 5 packs are each just under 600 pounds. So removing 2 of those if you don't need the range really helps your maneuverability, and also boosts, gives you a lot more extra usable load. Let's see, flight control systems. So this is a completely fly-by-wire aircraft. There's no pulleys or cables or turnbuckles or any of that. So for maintenance and pre-flight and 100-hour and annual inspections, really is simple in that regard. We have here in the flight deck pedals, but these are just brake pedals. These are not your rudder pedals. Differential, one side and then the other side, and then you have your joystick right here. If you notice, it goes down and up, left and right, just like a regular stick would, but it's got another axis in it. That's actually your yaw. So the rudder is in the hand. Everything is done with your one hand there. You have your trims, your push to talk, your autopilot disconnect, trim reset, and then this right here is actually your throttle. So this little scroll wheel right here, that's idle. That would be full throttle. And then we have regen going backwards, which basically adds torque onto the propeller when it's windmilling. So what you can do is, as you're descending, you can bring that into regen that creates more drag on the motor and harnesses that electrical power and creates a disc area around the propeller to slow you down. Yep. So we don't have flaps or spoilers or any of that on this aircraft. It's just standard ailerons, elevators, and rudders. But people always see right up here, you can see we have split ailerons on each side. So the aircraft has 2 ailerons on each wing, 2 elevators on each empennage, and 1 rudder on each tail. You can see they're drooping right now because they're fly-by-wire and the aircraft is off. So it's just an actuator and a dampener directly connected to each control surface. In normal flight, your ailerons move together just as if they were one. Your elevators move together just as if they were one, and your rudders are paired together as if they were one as well. So what we do for splitting them is for redundancy. The outer ailerons are on an A bus, and the inner ones are on a B bus, the low voltage bus. So they're redundant in 3 ways. They're geographically redundant, electrically redundant, and physically redundant. So geographically redundant, if you were to have a bird strike or something jammed in the hinge line of this aileron, you still have full other aileron on this wing. Electrically, the A bus is run on the front spar and the B bus is run on the rear spar. So if you were to have another bird strike or whatever, or to sever an electrical wiring, let's say up to the front spar, you would lose just your outer ailerons or just your inner ailerons, and you would still have full control in the roll axis. That goes for the same as the elevators. They're on different buses as well, and the rudders. So geographically different locations. Electrically, the routing for the wires are totally separate, and physically you have a whole other set of actuators, dampeners, hinge lines, all that stuff. If you were to have some sort of mechanical failure, you'd still have full control of the aircraft. So safety-wise, that's a big one for us. And it being a fly-by-wire aircraft, it can be a little spooky, right? Because your control stick isn't really connected physically, as a pilot would think, to anything. So having that XXX redundancy is super helpful. We also run 3 FCCs that all talk to each other and compare each other's values before they send any commands to the actuators. So a lot of redundancy there as well. Coming back around, just because we get a lot of questions about it. The fairings of the landing gear here, how they have these big gaps. Those gaps, as soon as the aircraft lifts off the ground, the landing gear relaxes and all of these fairings go flush for airflow, and then as soon as you touch down on the ground, they open up and help with cooling, remove heat from the brakes. Here on the passenger variant, we have this cargo bay for luggage. Coming right around, on either side of the aircraft, we have a NACA duct. This is air intake for cooling the engine inverter, motor inverter. There's no liquid cooling back there. It's all done by these 2 NACA ducts. Come around, you can see our split elevators as well. Just like the ailerons, obviously fly-by-wire, so that's our gap tape catching, but just free floating right there, and we got rain down last night. Our motor and inverter, everything fits in the aircraft in this zone right here from the fire. You could call this your firewall, if you will, back. So the motor is really only about that wide, and then you have your 2 inverters, 1 left and 1 right. Our high voltage system, just like the low voltage system, is split up into 2 sides. We have 3 packs on one HV side and 2 packs on the other HV side, and they're separate. So if you were to have a short or a battery malfunction or even a physical problem like a lug for one of the HV connectors failed in some way, you would still have full power to the motor. It comes to the electric motor just like geographic redundancies in the actuators. We have HV wires, 1 set run underneath, and the other set run above. So if you were to, again, have some sort of strike or something severed a wire, you have a full another set of wires that are powering your motor in a different spot. Another NACA duct there. On this side, you'll see these little ports labeled battery exhaust. So these are just little stickers covering blowout holes. So if you were to have a battery in a runaway state or an overheating battery that's causing problems, inside of that battery is titanium enclosures that direct the exhaust gases from each individual sub-pack inside of the pack out and away from other cells, other sub-packs and other packs, and blow it out of these hatches right there. And basically what that does is it buys you time before the runaway runs away, per se, to ignite other packs. So we've done tons of tests on these batteries, including a fully charged drop test 50 feet onto hard pavement and didn't run away. Yep, and the titanium enclosures are really what do that. They direct the hot gases away. You can't restrict them, you can't bottle it up, right, because it's going to run away. You just need to direct that hot gas away from other cells and other sub-packs in the pack to get your safety margins. So we're super proud of the safety systems we have, both in redundancies and with battery safety through our high voltage exhausts. Here's our charger, CCS1. On our ground-based infrastructure, we can charge at 320 kilowatts. The aircraft holds about 225 kilowatt hours on board, fully charged. Bottom or top of reserves is about 45 kilowatt hours on board. Ella will talk more to that as the pilot of what she plans for. That gives you your VFR reserves. This is also an IFR capable airplane, so obviously you need to factor in more reserves if you're flying IFR. Aircraft has a max gross takeoff of 7,000 pounds, 6,999 pounds. Empty right now, as you see, is just about 5,800 pounds, and about half of that is the batteries. So that's where, when you can do missions on fewer packs, if you don't need the range, it's really helpful. Just, you don't need to carry that weight around. You can drop key packs depending on how you want your center of gravity to be in the aircraft, and you can complete your mission more efficiently, obviously, without carrying all that weight. A lot of people ask if we are FIKI capable, flight into known icing conditions. Currently, with this aircraft, we are not. We knew that we would have to draw a line in the sand at some point and just say, this is our aircraft that we're going to move forward with and start certification. But we know that in the future, we're going to want to do things like FIKI and other mission developments like that. So we made this aircraft with removable leading edges all the way across on the wings and the empennages. So it would be a weeping wing TKS style is what we were going for in the future. Yep. So things like that we can look forward to and say, hey, we really need to get to market. We need to produce something, because you can just optimize forever. Every single day batteries are getting better. And if you constantly keep putting the greatest battery in it, you're never going to get to go flying. So you're just going to be changing batteries the whole time. So you kind of just need to say, hey, this is a great setup. This solves for a lot of people's missions. Let's get it to market. Let's build these. And if you can do that while thinking ahead about what customers will want in the future, like FIKI capability, we can accommodate that pretty easily. So although we're not FIKI capable right now, we do have some anti-icing accommodations, like heated pitot tubes, heated AOA vanes there. Both sides of the aircraft have those. So they're on two different ADC, air data computer systems. We have two different sets of static ports as well. So the computers are constantly comparing their values to get the best information to the pilot through to the G3000 Prime that we've got in the cockpit, that then ultimately lets the pilot make the best decision possible. Up in the nose, we have a a caster ring nose wheel that's steered by differential braking. We have obviously regular landing light, navigation lights, strobes. One of the kind of funny things that we have, one of the problems that you wouldn't think regular aviation is safety-wise. So when we turn our aircraft on, we idle it. Even though the airplane doesn't need to idle, the prop could be stopped, doesn't matter. But for safety reasons, you wouldn't know if somebody was going to dial it up right now and taxi away at any point. So what we have set is a 70 RPM idle. So when Ella will explain the flight controls on the display there, but when you enable your engine A and engine B, which are your two inverters per the motor, it idles at 70 RPM, which is a negligible power draw for the batteries, so you're not wasting electricity. But that, along with a flashing strobe, will tell everybody around that, hey, this airplane is active and live, because otherwise it just looks like it does right now, looks and sounds exactly like it does right now. One of the really cool flight planning things about this aircraft is that you can get in it, and the thing that takes the longest is just waiting for the panel to come alive. There's no warm-up period. You just go switch, 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 switch. And if your flight planning's done, you just go. So as you're flight planning, you're not burning any fuel. You can have the doors open. It's not loud. You don't need your headset on. You're just sitting there peacefully doing your your pre-flight stuff. It's a carbon fiber composite structure with a lot of aluminum and titanium joints where parts meet and where we need doublers, but the spars and all the skins and all the leading edges are carbon fiber. Nose bolt, wheel pants, interior is all carbon and composite construction. So we really we started with our proof of concept aircraft a couple years ago, and we learned through that because the batteries are heavy, you need everything else to be top-notch. You can't spare any extra weight on non-necessary items on the aircraft. So you really need to optimize everything to get the efficiency out of the electric propulsion system. And that's part of what blends to the funny shape of this aircraft is, although it looks weird, it is uber efficient. It's a great glider, about 16:1 glide ratio. On a 3.5 degree glide slope, you're actually accelerating at idle. So you need to go into regen, which is great because you get your little energy back, and that's how you maintain that glide slope. So people often ask, like, you're running pretty small wheels, why are the wheel pants so big? Well, you're landing gear fairings so wide, all that kind of stuff, and what it is for efficiency. If you can expand the length of your wheel pant per the height, you can keep the airflow laminar around it, and that's much more efficient than if you were to have a bulbous, shorter wheel pant, and then you would have turbulent air behind it. So that's a big part of what lends to its shape.
Hi, I'm Ella Brisson. I'm a flight instructor, demonstration pilot, and curriculum developer at Beta Technologies. We're here today at Oshkosh 2025 at the Beta booth, and behind me I've got Beta Technologies all-electric CX300 aircraft. Now this aircraft is our conventional takeoff and land. We've also got a vertical takeoff and land variant that's coming off the production line in a couple months. We're super excited about it. Let me tell you a little bit about the aircraft. So we actually flew 2 of these conventional aircraft all the way to Oshkosh from Burlington, Vermont. We made a bunch of stops and met a bunch of people along the road. It was a really fun road show. We'll get about 215 nautical miles of range. We'll typically fly for about an hour and a half, 2 hours, and we'll generally cruise right around 105, 110 knots. It's super cool because, you know, most people, their immediate question is, well, what about the charging? And we've got a really awesome charge network up and down the East Coast with and into the Midwest and California, over 50, 60 chargers implemented at airports already. But when we're on the road like this, we've also got some mobile charging options. And charging on these aircraft takes about 50 minutes from VFR reserves to 100%. So we're able to really, get these out in the wild, get them across the country, and keep showing people that electric aviation is happening right now. let's hop in here and take a look at the things that we've got available to us when we're flying. So as you can see, it's a super simple, super comfortable design. Kind of the first thing that most pilots will notice is that down here, we've actually only got brake pedals. Most people kind of get thrown for a loop by that, but the really cool thing about CX300 is that it's full fly-by-wire flight controls, and we now have all 3 axes controlled in our hand. So that means to get yaw, you're twisting your hand in the joystick like this, pitch just like this, and roll like this. So everything is really centralized here. You can fly with your feet flat on the floor or crossed in front of you. It's super comfortable, it's super intuitive, and it's highly responsive. Over here, we've got our control wheel, and this is how the pilot is changing the power demand and torque of the aircraft. So moving it forward, just like a throttle, you're applying more thrust, and that's how you go. You'll also notice that in the idle detent here, we've got a little bit of space behind the idle detent. So the pilot of this very slippery aircraft that does not have any flaps can actually pull back the control wheel and enter a drag regime of command. So what this means is that we're actually able to slow the propeller down and therefore generate more drag, and that's how we can get the aircraft to descend quickly. Up here, you'll see that we've got a really awesome Garmin suite. It's called the G3000 Prime, and we've only got a handful of switches on the panel here. So this is pretty much everything that the pilot is interfacing with. You'll notice we've got kind of our low voltage and our DC-DC converters up here, our high voltage battery switches connected to each battery pack specifically, and then our engine A and B switches. Up here, this is pretty much everything that the pilot's interfacing with. It's a super simple, super intuitive panel. So basically up here we've got kind of our low voltage section with our DC-DC converters that are taking our high voltage, converting it down into usable low voltage for our avionics, our lights, stuff like that. We've got our high voltage battery switches that are each connected specifically to their respective battery pack, so we're able to manipulate the packs as needed. And then down here, these 2 push switches are basically our push to start. So that's how you turn the engine on. You just press those in and the thing whirs to life. It's really, really cool. So if you're curious, I can go ahead and turn on our LV battery here. We'll wake up the G3000 Prime, and we can take a quick look at kind of the work that our avionics engineers put in with Garmin in order to make, typical synoptics make sense for electric aircraft. Obviously, we're no longer monitoring things like oil temperature and pressure. Rather, we're monitoring things like battery temperatures, motor temperatures, etc. So you'll notice the panel's just kind of waking up here. We're not going to get our AHRs or anything without everything else woken up, but we can take a quick perusal through the synoptics and just see what they look like. First up, we've got our engine synoptic. So here it's super simple. We're monitoring motors, inverters, speeds, and torques. And we've got our temperatures up here. And this is pretty much where the pilot is looking to understand what % torque they're setting using their control wheel or their throttle.